Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we'll start this session. So it's a talk from the University of Rutgers, and Amélie is presenting. Maybe I should put you on, right?
Okay, is the mic on? Okay, great. Okay, so this is work I've done with a graduate student at Rutgers, Minji, who was here today, and we implemented the system. The goal of this project is to improve search query results by taking into account the fact that several sources, web sources, would corroborate the same information. And the fact that several sources give similar information gives higher quality to the information you're looking for. So many of us come from a database or information retrieval background, and the type of query model we're used to is either a standard database query model where we return a set of tuples that match the query exactly. In information retrieval, we're used to a query model that returns a list of documents that are closest to the information needs of the user, and that's what standard web search are doing. When you're inputting some keywords to a search engine, what you're returning is a list of web pages that are considered to be relevant to your query. It doesn't give you always an answer to the query, and users then have to go to all individual web pages to retrieve relevant information, and sometimes have to go through several web pages to check and compare the information. So both query models are insufficient for the information needs because we want to be able to compare what different sources will tell us to make sure that the information is high quality information. There are several new query models that have been used and studied. Notably in database systems, you have Topk query processing that provide a more IR type of query model to standard database functionalities. And in question answering, you actually have some of this corroboration, but most of those systems, most systems except for question answering systems, consider answer individually. Some question answering systems do take frequency of the answers into account, and we've seen Kevin's system today that also takes more information into account. So it's not, this block is not completely true today anymore. If you look at web information, there are many reasons why we want to go and corroborate information from different pages. The information on a single page may be wrong because it's biased. Different car manufacturer will have biased information about its car because it wants to sell the car. The information can be erroneous. People who entered the information may have made mistakes. Many pages are outdated. There's a lot of very old information of the web. And some information is misleading. That's extremely true, for instance, if you consider any political website or political blog. So users like to check different websites to confirm their information. And rather than having the user, letting it up to the user to go to each individual website and corroborate the information, can we do that automatically by having an interface that would get the information from those websites, aggregate it based on some scoring function, and then provide it to the user? Am I just pressing this thing randomly? Okay, so that's an example of a query where corroboration will be useful. If you ask the information for the gas mileage of a Honda Civic 2007 on MSN Search, you will get a list of websites. The first two websites, you probably cannot see it from the back, but are Honda.com websites. And they actually give you slightly different information from different pages on Honda, 51 miles per gallon, 33 and 38. Then you have two hits from the other websites that give you 40 miles per gallon or 30 and 38. There are some context information here, gas mileage on highway or gas mileage in city. That's why some web pages have more than one. Car.coms give you 30 and 40, and you have some other websites that all give you slightly different information. So now what is the correct gas mileage of the car based on this information? Of course, there is no perfect source that gives you the gas mileage unless you decide you trust exactly one source. So what we're trying to do is find a consensus among the sources, but also weight how much we trust each individual source. So that the...
Do you have it on timer?
No, I don't have it on timer. So, it's probably a previous version of PowerPoint. I don't know if the transition... Okay, that's fine. So here, on this example, would you trust results given to you by the Honda.com website? Do you know anything about the AutoWeb.com website? How much do you trust each of these individual websites? Are all these values referring to the correct year of the model, the correct type of mileage you're interested in? How do you aggregate all this information to provide an answer to the user that is correct? So one way to do it is just do a simple frequency. We would get, here we aggregated things based on gas mileage range, and gave the percentage of sources that provided value in that range. Frequency is fine, but then you leave the door open for spamming and link farms and a lot of malignant users on the web would just input more and more information so that you'd have to push up some results they want to have. So frequency is an important aspect of the importance of an answer, but we have to consider more. We have to consider how much we trust the website, how much we trust the information within the website. And so we presented a corroboration system that uses multiple parameters in this work. And this is, so these slides are based on some work that was presented at WebDB last month, and it's some preliminary results on the web corroboration's work. So what are the challenges for doing web corroboration? The first challenge is to extract information from the web. And as it turns out, it's a very difficult challenge. I was sort of naively expecting to have many available tools to extract information from web pages. And by the way, if any of you have any links to available such tools, I'll be happy to to talk to you. But it's actually pretty hard to accurately extract good information from the web that match a given query. And the part we're focusing on is the second challenge, which is designing a meaningful scoring function. How are we going to aggregate answers, and what do we want to take into account when we're aggregating answers? I mentioned the frequency of the answer in the result set, which is an important aspect that we should take into account. But you should also take into account the importance of the web pages that provide the answer. So one aspect that we consider is the importance of the web page. No idea what this is. As measured by the search engine. This is because that's the only information we had available. We don't have, so we had the MSN rank of the web page, but we didn't have any information how the rank was given and how you score things internally. Another aspect is the importance of the answer within the page. And that is based on the formatting instruction within the page, whether or not there are multiple answers in a page. If there are multiple answers, we should reduce the scores of each individual answers, because each answer we get from that page is probably lower value. In the presence of multiple answers in a page, the proximity of the answer to the query term can give us an idea of how good this answer is related to the query term. Okay. Another aspect, and to reduce the effect of malignant people just putting copies of the similar web pages to increase the results on the web, we want to take into account the similarity of the page with other pages. If we get the same information over and over again from pages from the same domain, then it's likely that they come from the same source, and we don't want to push up the result as much as if they came from completely different sources. In the same way, we also want to reduce the impact of pages that seem to be copy-paste information. A lot of websites now are copying Wikipedia entries, for instance. So if all those pages are just parroting each other, yes, the fact that many people took the time to copy the information should be taken into account, but it shouldn't be as important as having novel information that corroborates the previous information. So we use a dampening factor to reduce the impact of pages from same domain or copy-paste pages. And the last challenge is how to select the result set. Of course, we will not be able to go and parse the whole web to figure out what the whole set of answers. So what we did is we considered the search engine query results and decide to access it in order. And the question is, how deep in the search engine query results should we go? Remember that we're taking into account the importance of the web page as given by the search engine rank into a scoring function. So the lower we get, the lower weight those new pages will have. OK. So for the first challenge, information extraction, we actually limited ourselves to query containing numerical information. And there are two reasons. One, as I mentioned, we had problems finding good tools for information extraction. So we wanted to have a prototype running soon. And this was an easy way to have an information extraction tool. Numerical queries tend to have answers that are easier to identify in the text. For instance, in the mileage query, an answer will be of a type X MPG or MPG of X. So we considered that. We also analyzed the MSN query log and discovered that those type of queries tend to have a higher click-through than the overall queries. And that could be for several reasons, but it tends to suggest that for those type of queries, people will tend to check several websites. So that those are good candidates for corroboration queries, because people for mileage or length query will tend to check different web sources to compare the information, more so than for standard queries. We also focused on queries without an agreed upon correct answer. For example, the mileage query. There is no exact answer for the mileage query of a 2007 Honda Civic. However, our techniques work for queries that do have an agreed upon correct answer. What's the length of the Brooklyn Bridge? It's just that it was less interesting to consider those queries because most sources will return the same length. OK, so some details about our scoring functions. Once we extract answers, we score both the pages and the answers within the page. And the score of an answer for a given page is based on the score of the page and the score of the answer within the page. So the score of a page is based on the importance of the page. As I mentioned, the only information we have on the importance of the page, because we don't have access to the underlying search engine results, is the rank of the page in the search engine query results. If we had access to some scoring information, we could have some more fine-grained scores. And we use the parameter alpha to quantify the importance of page. Basically, we're dampening the weight of new pages as we go down the search engine query results. So the idea is that the top page will have the most weight, and as you go down, new pages will add information that has lower and lower importance. So one thing to keep in mind is that the way we parameterize alpha has an importance on the number of pages retrieved, which we will see in experimental results. We also, for how to score a page, the weight of the page is based on the duplication between pages. And for this, we dampen, as I mentioned before, pages that have information that we have seen before, either in pages from the same domain or in pages that have a very high similarity in terms of copy-paste. So we just compare text information and did an edit distance for the copy-paste information. And for this particular prototype, what we did is we just halved the weight of pages that were duplicated incrementally. So the first duplicate page will have a weight divided by 2. The next one will have a weight divided by 4, and so on. So combining the importance and duplication, we get the score of the page. Now for score of individual answers within pages, we consider the number of answers we can extract from a given page. The more answer we extract, the lower quality those answers are. So one simple way would be to just divide the score of the page by the number of answers. However, this just assumes that all the answers within the page are equally relevant, which is unlikely to be the case. And you have many pages that will list, for instance, for the car example, many different cars with many different mileage information. So we actually use the distance of the query keywords with the actual extracted answers to weight the different values. And this is still very rough, and we need to improve a lot our information extraction techniques to make it to retrieve answers with higher quality. And so based on, we take the distance into account and use that as a weight to score the individual answers within the page. So the score of an answer in a page now is the product of the score of the page and the score of the answer within the page. And to score the individual answer, we just take the sum of all the scores that these answers has gotten from different pages. This is a simple frequency. This is a simple way to consider the frequency of the answer. So the last challenge, selecting web pages. As I mentioned, we don't want to go through the whole web. We have to stop at some point. So because we're considering the importance of pages as a way to weight the score of answers from those pages, at some point, new pages will not give us much information. So we can actually dynamically stop retrieving new pages from the search engine query results when we know that the additional score that we get from those pages will not make any change to the final answer, the top K answer order. So what we use in our experiments is it will not make any change to the top 1 answer. So quick preliminary experimental evaluation, we selected 14 numerical queries from the query logs, and we selected queries that had numerical parameters and that had more than 1 click for information extraction. We evaluated the costs of the corroboration and used the user clicks, so the query logs, to assess the quality of our results by comparing the pages users clicked on and the pages from which we retrieved our top 1 answer. And we also considered the number of pages retrieved, how deep in the search engine query results should we go. So if you look here at the results, they actually don't, in terms of time, they don't look that impressive. It's between 20 and 30 seconds. So keep in mind that we did these experiments not optimizing for time, and we retrieved pages sequentially. So an obvious optimization would be to do some parallel retrieval of web pages. So that would definitely speed up query time. Corroboration takes a few seconds, which we also could improve with some parallelism. But if you compare it to the time that users spend actually clicking on web pages and comparing information from different pages, it actually might be a price that people will be willing to pay to get corroborated information. The second experimental results, and that's actually going to tie in with the last slide, the assets, the good, the bad, and the wanted. So one of the problems we had with the assets is we wanted to use them for a quality evaluation, comparing the user clicks with the pages from which we extracted the information. And as it turns out, between the time that the assets were retrieved and we started running experiments, the web had changed a lot. And so out of those 14 queries, only 7 still had URLs that were present in the search engine query results. And we got some, Evelyn provided us with some text information, the data from the links, but they were also taken a year after the assets. So we there was some problem trying to figure out the there was a mismatch between the clicks that we had at the time and the results. But if you look at those 7 queries, the first, the blue line is the total number of user clicks for those queries. The red line is the number of user clicks that still appear in the search engine query result in the top 50. The yellow line is the number of clicks that from which we were able to extract answers. It's actually pretty close to the red line. We don't know whether it's because some of those pages don't have the answers or because our information extraction technique is still too rough to extract all of the answers. The last one is the number of such pages from which the answer extracted ended up being in the top 1 answer. So you can see there's a high correlation there, which is that we were able, by looking at answers from every page, to still find answers that the user manually would have selected from web pages. In terms of the number of pages retrieved, as I mentioned, it's very dependent on the parameter alpha. The high alpha is the more dampening factor we have on new web pages, and so the fewer pages we're retrieving. We capped the number of pages retrieved at 50, but you see that even with a very low alpha, not all queries will require us to go through 50 pages because top answers will tend to populate up faster than going through the top 50 results. So we converge faster than 50 pages usually. So this is, we're currently implementing an interface. So this is a snapshot of the interface. I didn't have Kevin's courage to have it online here. But you can see, but you can see on the left side, we have standard query results. And then users have the option of asking for corroboration, and we will return the corroborated data. In that case, we have data ranges of values, and with all the web sources from which we extracted the data and how many occurrences of the answer we could find in the web source, and then you can click on the individual web source to see the answer in context. Okay, so as a conclusion, we're still improving on this work. Specifically, we're improving on the scoring mechanism, and we're working on having a more robust probabilistic framework to score individual answers and to score the importance of web pages. We also want to improve the evaluation by comparing with more user click-through, improving, adding to the number of queries. This is, of course, limited by our information extraction, so we really have to expand on the type of queries that we can extract. And, of course, improving query processing time by using parallelization. So, as conclusion, this corroboration work can actually be used in different contexts, not only in web search. There are many applications where there's a large amount of low-quality data, and rather than having to rummage through a lot of information to try to figure out which one is the good information, combining information from different sources and aggregating it based on some probabilistic framework would drastically improve the quality of results returned to the user. And fortunately, it hasn't been used much in practice, so we're hoping that it's going to have a large impact on answer quality in many applications. We use standard ranking techniques such as top-K query processing, but they have to be adapted to a corroborative framework because the query model is slightly different from what people have been used to, where individual answers can be scored separately. We show good performance in both time cost if you compare to what is the current user experience, and in quality of answers when you compare it with user clicks. So let me skip the related work and go to the quest for assets. So as I mentioned, the good part about the query log is that it gave us something to assess the quality of the corroboration framework, which was an invaluable tool for that. The problem is that we didn't have the connection between the actual results and the clicks. And it would have been nice to have, the data at the time of the clicks. what would have been nice as well, it would have, in addition to the rank of each individual URL in the results, having some idea of what the score would have been, even if we don't have the internals of the score, because I'm assuming the distribution of the scores is different depending on queries, and in some query the difference in score between the first and the second page is low, whereas in some others it's higher. So we could take that into account in how much weight we put in web pages in the corroboration. For the wanted, I sort of put a wish list. So the text content of pages available in query logs would be nice. It would be great to have user personalization information if it is available. And I know that there's a lot of privacy issue there, especially with the AOL debacle of last year. But having information about what the user clicked on in previous sessions could help us boost the pages that users tend to trust. And also having some user feedback on corroborated answers.
Two questions. Could you switch to slide 19, please? The one with data items. Possibly I misunderstood it, but as I can see, number of clicks in answers and number of clicks in top of one answer are almost identical. Is there any reason?
Yes, they are almost, actually they are identical in all those cases.
What does it?
So it's a very small set. So it could be non-representative.
So it means that all documents contain top one answer.
It means that all the it means that all the URLs that user clicked on contained an answer that we found was the top one answer for those 7 queries. But we extracted answers from more documents, so it just means that the users were good at finding the good documents.
And the second question, did it take into account numerical distance between values? For example, if one website says that mileage is 35 mpg and another one says that it's 35.1.
So that's a very good question.
What website says it's 50.
So what we did is that we took into account range information between value, but we statically selected the ranges. So in your example, we would have ranges between 35 and 40 in the same bucket, so they would have been taken into account. What we're also working on is adding some dynamic selection of ranges, so that you could have different bucket size based on the distribution of data, of answers in the result set.
Brian Davison, Lehigh. So you looked at duplication of pages. How about duplication of answers? Because you can have the same answer in many different formats on the same site.
Right.
So I'm wondering
so it actually, so yeah, I went over it quickly, but the fact that the same answer was, let's say you have three answers in the page, and one occurs twice, it would boost it. So we would count it twice as that particular value. But there's definitely some more that we can do there, especially having score associated with the extraction, score associated with the distance to the query, and so on.
Okay, last question.
Go back to the last slide, the last one. So so I think this is very interesting, and you are now taking an approach of building upon current search engine. Perhaps you are using the MSN SDK. So I want to ask a question that's similar to what Shulman proposed in the end of his talk about the search API. So for supporting corroborative answer like this, do you think if the API can be supported in a more advanced or something that different, it will facilitate the this task?
So let me see if I understand the question correctly. What we've been doing is doing it on top of the search engine. So after the results, would it be helpful to do it integrated in the search engine? Or
if search engines support different API?
Yes, definitely. If we had, for instance, if we had access to the search engine indexes, we wouldn't have to parse the web pages individually, and we could take that information into account. That's, of course, okay. So we hope that that's what we hope. We also would have information about how the pages are scored, which we could take into account as well. So we would take off one level, so it probably would help a lot.
Thank you.